Yes, sir.
Okay. So now we have Fermi gas. And in Fermi gas, if you remember the degeneracy parameter A, which is 0 here and large value here, here it is 1. So now I am very, very close to this. Okay. I am very close to this. That means that I am going to take the temperature to be almost very, very close to 0. The temperature very, very close to 0. So please understand this case of Fermi gas, kind of ideal case, because you are very, very close to 0 Kelvin temperature. That is not in practice. In practical situations, even 3 Kelvin or 4 Kelvin is a very, very low temperature, and you require a lot of other things to produce such a small temperature. But theoretically, let us discuss the Fermi gas when we are very close to this, and the many definitions will come out of this that we will have to remember as an ideal case. Okay. So again, I will take the same Fe that you already remember for fermion. What was Fe? It was equal to 1 upon A e to the power beta e and plus 1, right?
Yes, sir.
And A is actually e to the power
Minus alpha.
alpha,
Minus alpha.
and this is equal to e to the power minus mu by kBt. Okay. So this is the equivalence, and mu is chemical potential. Mu is chemical potential of that gas. Now, if I put it here, this chemical potential is a function of temperature. Please remember, the chemical potential is a function of temperature, and if you are very, very close to 0, then you can take this almost as a constant. So mu of 0, it does not mean that t is equal to 0. It means in this very, very close region, okay, when you are very close to 0, almost this value of chemical potential will become constant, right? And that constant will become the Fermi energy. Is that okay? So when
Sir,
Yes, sir.
this chemical potential is actually a function of temperature, and when you come very, very close to 0, then you can take almost chemical potential as a constant, and that is known as Fermi energy. Yes, anybody was asking anything?
सर ए ई पावर अल्फा होगा ना, नेगेटिव अल्फा शायद नहीं होता.
अब किसी ने बोला यार, मैं तो लिख रहा था अल्फा ताकि ऊपर जाके माइनस अल्फा हो जाए. भाई
यस सर.
व्हाट इज फर्मी डिस्ट्रीब्यूशन? ऐसे याद रखो, Fermi distribution is e to the power minus alpha e to the power minus beta e. So when this will become very large, this gas will also behave like a Fermi gas. Okay.
Yes.
So now this is okay now?
Yes.
Okay. So this concept is okay to everyone?
Yes, sir.
We will see finally also
Yes.
that mu is an infinite series consisting of temperature, and if you put t is equal to 0 or t very, very close to 0, so you will get the Fermi energy. So this Fe, which is actually Ni by Gi, okay, this will become equal to 1 upon and e to the power beta e minus Ef and plus 1. Yeah, is that okay?
Yes, sir.
So this is number of particles per unit quantum state, and this is given by this formula. And please just understand that here also you have beta is equal to 1 upon kBt. Does not mean that you put t is equal to 0. Okay, that means we are close to this, and we have already adopted mu naught is equal to EF, but still we have capital T here. Okay, because now we have to discuss everything here. So here, very close to this, still we will get many cases, right? So that all we have to discuss. Now please see, if I take E greater than EF, दे देखना ध्यान से, बहुत ही इंटरेस्टिंग मैथमेटिक्स है. If I take E greater than EF, what does it mean? That you have different energy levels formed within the Fermi gas, and suppose this is the Fermi energy, right? And this is the energy levels that are above. There are infinite energy levels, no scarcity of energy levels, right? We have so many energy levels, correct? Now, if you are E greater than EF, then E minus EF will be a positive quantity. Am I right?
Yes.
It will be a positive quantity. And if T is very small and this is a positive quantity, then you can see that Ni by Gi will become 1 upon e to the power infinity plus 1. Please say this.
Yes, sir.
Yes, sir.
So Ni by Gi, this will be equal to 0,
Yes, sir.
right? So that means if you move, and this all discussion is at t is equal to 0, don't forget. Okay. So if you move near t is equal to 0, and if you move above Fermi level, you will find that all are empty levels, right? All
Yes, sir.
empty levels. समझ आया सबको? Because
Yes.
number of particles per unit quantum states is 0. That means no particles are available here. Now go for another case. E less than EF, below Fermi level. So then what will happen? E minus EF will become negative, right? And Ni by Gi will become 1 over e to the power minus infinity plus 1, which is equal to 1. That means Ni is equal to Gi. That means every quantum state will have one particle. Can you see that? So that means in that case, when E is less than EF, you will have all filled. What you will write? All filled state.
All filled.
So that means if I make a figure, a diagram out of this, so what will be this? It will be, this is the Fermi level, and these are the levels below, right? Suppose this is the lowest level. Okay.
Yes,
So there are levels above. So you will have all the filled states. at t is equal to 0. So this will be the picture. At t is equal to 0, below Fermi level, all filled state, and above Fermi level, all empty states. Correct?
Yes, sir.
Yes,
So
sir.
here, for this, your calculations will become very, very simple because of this. Because of this, your calculation will become very simple. Why? Let us see that. If I take Ni is equal to what we got, Ni by Gi is equal to 1. So Ni is equal to Gi, right?
Yes, sir.
This you will agree.
Yes, sir.
And if I take it as a continuous, so Dn will be equal to Ge. Yes,
Yes, sir.
Yes, sir.
Gn will become Ge. So Dn will become, tell me in 3D, what is Ge?
The 2 pi v
2
upon
pi
h
s
cube.
p 2m by
2
h square to the
pi
power 3
v
by 2
2m by h square
to the power 3 by 2
to the power 3 by 2 e to
e
the
to the
power
power half.
half and de. This will become dn.
Yes, sir.
So if I want
sir.
to write total number of particles, it will be 2 pi v 2m by h square to the power 3 by 2 integral 0 to ef, because there is no particle above ef. So limit will only extend to 0 to ef. And this will give me e to the power half and de. You agree with this?
Yes, sir.
Yes, sir.
So n will become 2 pi v 2m over h square to the power 3 by 2 e to the power half plus 1
3 by 2.
over
3 by 2.
3 by 2, and upper limit being ef, it will become this. You agree with this?
Yes, sir.
Yes, sir.
So you can write from here the value of ef is equal to, tell me, calculate the value of ef from this. If you want, you can just put this as 2 pi sv to just accommodate the multiplicity.
Sir, 3n upon
2 pi sv.
sir, am I audible?
Yes. Tell me, what is the
Sir,
value
it
of
is
ef?
sir, 3n upon 4 pi sv
4 pi sv
to the power 2 by 3
to the power 2 by 3
into h square by 2n.
h square by 2m. So this is the Fermi energy. Please see this. The Fermi energy, this Fermi energy is just depending on the number density to the power 2 by 3. Correct?
Yes, sir.
Fermi
Yes, sir.
energy. And because of the Fermi energy, I can define Fermi temperature also. Fermi temperature just corresponding to this Fermi energy, because EF can be written in the form of temperature also, right? We have a formula associated to kBT. So if this is Fermi energy, this is constant, this is the corresponding temperature that will be called Fermi temperature. Am I right?
Yes, sir.
And similarly, you can define Fermi momentum. Fermi momentum. Because you can define Fermi momentum as under root of 2m
2 MeV.
EF for free particle. And so you can also see here a very important point, that the Fermi momentum will be proportional to, because of this root, 1 will be gone. So it will be proportional to n to the power 1 by 3. Right?
Yes, sir.
So Fermi temperature, Fermi momentum, and Fermi energy. All three we have defined. Any doubt in this?
No, sir. No, sir.
So we can what we can do is now just explaining this Fermi energy, because you can see there it is all filled, right? This Fermi energy. So please understand this. If the system of fermions is cooled to temperature very, very low, the highest energy available, if there are many particles to be filled, they will be filled. And suppose this is the highest energy level in which the particle is there, that will be called the Fermi energy. So Fermi energy is the highest energy level associated to the system which is cooled to a very, very low temperature, very close to zero. So that will be called Fermi energy. If you want, you can write this definition.
Sir, can you say it again?
Yeah. If we cool the Fermi gas to a very low temperature, close to absolute zero, so particles क्या कोशिश करेंगे? They will try to go as low as possible in the energy, right? If you are cooling down the system to capital T is equal to 0, then the particles will try to go as low as possible. The highest energy level available in this case is called Fermi energy. The highest energy level available in this case is called Fermi energy. And if I plot what we have done till now, if I plot Ni by Gi, what I will see is that from 0 to EF energy level, this value is 1, Ni by Gi is 1, am I right? And after this value is 0. This is for T is equal to 0. And if you plot T greater than 0, then the graph will be coming like this and going like this. This is the graph when T is greater than 0. So you can see here that up to Fermi energy, Ni by Gi is 1. That means every quantum level is consisting of single particle. As you can see here also I have drawn. And after Fermi energy, that is absolute 0, because no particle is present above Fermi level. But all this is happening at T is equal to 0 temperature. But if you are watching the system at T greater than 0, then
सर ये Fermi distribution इस तरह से नहीं follow करेगा.
then there will be a distribution. That means there will be energy levels beyond EF also, right?
Yes, sir.
And you will get a very important quantity here if you can see, because this is EF. So at this point, energy will become equal to EF. So this will be half. Correct? This number is half. So what will happen if we increase the temperature too much? Then what will happen?
सर ये डिस्ट्रीब्यूशन क्लासिकल हो जाएगा.
So I mean not that much. Still suppose it is following e to the power beta e minus ef plus 1. यही है ना? This is the case.
Yes sir.
So suppose you have large value of t. T is very large. Then what you will find? So you can see that if t is very large, this value will become very small.
Yes sir.
So this will become e to the power 0 plus 1. So that means it will become half. Okay. So even if you put the temperature to a large value, this is the Fermi energy level. Half of the particles will remain here and half of the particles will go above the Fermi level. And this all will happen at a very large temperature. So जैसे अगर तुम
relatively है ना.
टेम्परेचर बढ़ा दो तो ऐसा नहीं होगा कि ये सारे पार्टिकल उठ के फर्मी एनर्जी के ऊपर चले जाएं, बट मैक्सिमम यही हो सकता है कि आधे फर्मी के नीचे रहें और आधे फर्मी से ऊपर रहें. ओके.
हाँ सर. सर ये सारा फिनोमेना स्टिल उसी रेंज में हो रहा है ना जहाँ पे वो केमिकल पोटेंशियल को EF मान ले रहे हैं.
No, I am not taking here E is equal to EF.
Okay.
If this value of temperature is suppose large, this kBT is large suppose, right? So 1 upon kBT will become 0, na? If kBT is much larger than E minus EF. Okay.
Yes sir.
So then also it will become 0 and it will become e to the power 0 plus 1. So that means only half of the particles will be above that and half of the particles will be below that. And if you really go very far, then obviously more and more particles will cross the Fermi level and you can have lower values of Fe. So this is a simple, derivation because of the approximation we have made, but this approximation also gives lot of insight. So is this okay?
Yes, sir.
Yes sir.
अब एक और काम करना है हमें. We have to relate Fermi energy to average energy. Okay. Fermi energy to average energy. Let us relate Fermi energy to average energy. How to do that? Any suggestion?
सर हमारे पास DN तो था ही सर, उसमें से E को मल्टीप्लाई कर देते हैं.
So if we want to calculate the energy, हमने number of particles, what we did, that U will become integral 0 to EF. क्या था expression? 2 pi SV 2m by h square to the power 3 by 2 e to the power 3 by 2 and dE, right? This was the
Yes, sir.
expression.
Yes, sir.
So let us integrate it quickly. Let us integrate it. So it will become u is equal to 2 pi sv 2m by h square to the power 3 by 2 e to the power 5 by 2 by 5 by 2. Okay. This is your average energy. So this is the energy. And what was n? n कितना आया था?
Sir, 4 by 3 pi.
4 by 3. 4 by 3 pi
pi SV.
pi sv
2m by h square.
2m
Power
by
3 by 2.
2m by h square power
Power 3 by 2.
3 by 2
EF की power 3 by 2.
ef की power 3 by 2. Okay. So let us get the average value now. Average value of single particle will be energy of the system over number of particles. So what will be the average energy? 3 by 5.
Yes, sir. 3
यहाँ
by
पे
5 EF.
यहाँ पे EF to the power 3 by 2 था ना?
Yes, sir.
3 by 5 EF. देखो आ रहा है? चेक करना.
Sir, आ रहा है sir.
सर आ रहा है.
So ये एक बड़ा ही important understanding है कि suppose you have a Fermi gas and you cooled it to a very very low temperature, and suppose the Fermi energy, which is the highest energy available in that situation, is 5 electron volt, and there are fermions in different levels. So what is the average energy of these fermions?
3
3
unit.
electron. So this is very very important observation. Is this clear to everyone? Absolutely clear.
Yes, sir.
So this was when you had T very very close, and on this same note we can up now you can see that in every case what will happen, you will go in that detailed derivation consisting of capital A, there will be infinite series and you have to manage everything, right? So उस context में अब इतने discussion के बाद last वाला result I would like to write directly for Fermi gas. So we have discussed so many cases. Now you have idea na how we can calculate by applying the approximations or infinite series within the integrals. All that idea you have. So now please write strongly degenerate. Still the case is strongly degenerate. Strongly degenerate. But this time t is not equal to 0, but t is greater than 0. Just let us do this. Strongly degenerate case when t is greater than 0. In this case, what will happen? By the same logic that I told you, the value of n will be 2 pi sv 2m by h square and 3 by 2 f3 by 2 a, and u will be 2 pi sv 2m by h square. ये सब कर चुके हैं ना हम लोग? f of 5
Yes, sir.
by 2a. So in this, when you apply the approximations, you will find that the chemical potential is equal to EF times 1 minus T by TF square pi square by 12 plus dash dash dash. This is a very important result if you can remember. The derivation is obviously, it will be little large. And the average energy expression is given by 3 by 5 and e to the power f 1 plus 5 pi square by 12 T by TF whole square plus dash dash dash. Now please see this. Please see this, that the average energy is, if you take T is equal to 0, what it will become?
3 by
3 by
5
5
3 by 5 EF.
You can see that now. So this is more
Yes, sir.
general
Yes,
case.
sir.
If you see chemical potential, take T less than TF or T very close to 0, then mu T will become
EF.
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 So all this result is like extension. इसी का वो special case है, you can say. And this is the generalized case when you are just T greater than 0, but it's still a strong degenerate case. That means you are close here, right? This is, suppose this is around T is equal to 0. So we are close. We are here, still strongly degenerate, but T is not equal to 0. Capital T is not equal to 0, right? So in exam, once they gave this expression or this expression and they have asked certain things. So please just understand this. The derivations gives you the idea how to do it. And sometimes the tough expressions are already given. Suppose I give you this and ask you about the specific heat. So you will have to just differentiate it with respect to temperature, right? Only this much expression is given. And somebody may ask you, what is the specific heat? So obviously you will have to just differentiate this average energy with respect to temperature at constant volume to get the specific heat. That is not a tough job. But important thing is कि ये सारे expressions आपके देखे हुए होने चाहिए, तभी आपको comfortable feel होगा. अगर ये आपने पहले से देखे नहीं हुए तो you will not feel comfortable. Okay?
Yes, sir.
Yes, sir.
So this was the discussion regarding the fermion. fermion के regarding ये discussion था इतना, और भी चीजें हमें करनी होंगी, बट फर्स्ट राउंड में इतना ही अब बोसॉन के बारे में पहले पढ़ना होगा, एंड देन वी विल मूव फॉरवर्ड. ओके, सो फर्मियन में पहले बताओ, इज देयर एनी डाउट, एनी प्रॉब्लम अप टू दिस लेवल?
No, sir.
So another type of particle will be there, that will be called boson, having symmetric wave function, having spin is equal to 0, 1 or 2 kind of spin, not as spin half or 3 by 2 like fermion. And those particles, the main difference is that fermions are one particle, one quantum state, jabki bosons are one particle, many particles can sit in same quantum state. So both are quantum particles, but depending on the spin, one is in the category of fermion and another one is in the category of boson. So what I will do again, I will write the omega of boson, right? I will write the omega of boson and then I will do
Yes, sir.
everything. So that will require, you know, the kind of effort is needed, right? थोड़ा सा बड़ा भी हो जाता है तो वो हम लोग नेक्स्ट क्लास में करेंगे, लेकिन फिलहाल एक क्वेश्चन मैं चाहता हूं कि आप करें मेरे साथ। क्वेश्चन ये है कि सपोज वी हैव 10 boxes, 1 2 3 4 dash 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 10 boxes and 10 balls. 10 balls. Okay, and so we can number them. Suppose the balls are first ball, second ball, third ball, fourth ball, fifth ball, sixth ball, seventh ball, eighth, ninth, and 10th. Correct? And the boxes are like this: first box, second box, like that, 10th box. Now the shape of the box is such that it fits only with the similar number. For example, the first box will only fit with ball number 1. The second ball box will only fit with ball number 2. And the 10th ball will fit with what?
Ball number 10.
10. Ball number 10. Ball number 10.
Ball number 10. Okay. Now I want a omega and b s. Can I calculate for such a system?
Yes, sir.
सर ये सर ऐसा तो कैलकुलेट नहीं हो सकता ना
Hmm?
सर ओमेगा 1 हो जाएगा तो एस 0 हो जाएगा
तो 0 है ना।
So what is omega?
1.
तो ओमेगा इज 1
Omega is 1. And what is
0.
s?
एस 0
S is 0. Very good. Now I take another case in which the balls, these balls are, suppose we have few balls in each case, right? In first case, what I did?
One box, one ball.
One box and one ball. Only one box will fit. But ऐसा भी हो सकता है कि one वाले कुछ balls हो, right? We can have. So please write.
सर एक बार रिपीट करेंगे सर
Just a second. I want ये इसको properly लिखवाना चाहता हूँ. Just एक second देना. Yes. Balls of 10 different colors. 10 different colors labeled A is equal to 1 to 10 are to be distributed among colored boxes. We have boxes which are also colored. Okay, like different colors are there, so these are also like this 1 2 3, the color thing. Okay, a ball can only go in a box of same color. And each
Yes, sir.
box, yes,
A ball can go.
a ball can, एकदम अच्छे से लिख लेना जरा क्वेश्चन ये. Balls of 10 different colors labeled A is equal to 1 to 10 are to be distributed among different colored boxes a ball can go in a box of same color and each box can contain at most one ball. So this, suppose Na is the number of balls and capital Na is the number of boxes. Okay, सेम कलर के, सो इसके Na है. ओके,
यस सर।
फर्स्ट कलर के कितने बॉक्स हैं?
कैपिटल एन
फर्स्ट कलर के कितने बॉक्सेस हैं?
तो 1 है सर।
नहीं नहीं, वो तो ये क्वेश्चन
N1.
खत्म हो गया. अब ये क्वेश्चन है, इसमें फर्स्ट कलर के Na बॉक्सेस हैं. ओके, N सफिक्स है. और फर्स्ट कलर की बॉल्स कितनी है? स्मॉल n. ठीक है ना, क्वेश्चन समझ आ गया?
यस सर।
क्वेश्चन की लास्ट लाइन जो आपने बोली,
एंड दिस इज मच मच ग्रेटर देन Na. हाँ बोलो बोलो.
सर मतलब
प्रॉपर्ली में लिखनी
हर एक का नंबर सेम है क्या?
बिल्कुल भी नहीं.
सर ये जो स्टेटमेंट
अच्छा
था ये
सर।
केस बन गई था.
बस मैं
हाँ,
एक
सर
सर।
डी
सेकंड,
जनरेशन का केस बनाया ना सर।
1 सेकंड. टेल टेल.
सर डी जनरेशन का केस बनाया ना सर ये तो।
हम्म check the group. Everybody. So the question is that the total entropy of the system. Very nice question. Let us solve. पहले बताओ क्वेश्चन सबको समझ आया या नहीं? You can ask again. Not to repeat me,
आगे सर समझ में।
but
Sir.
what you have not understood in the question, that
Na और कैपिटल Na हमने क्या लिया है वो समझ में नहीं आ रहा है। मतलब
क्या क्या चीजें हैं आप ये बताओ.
बॉक्सेस है, बॉल्स है, कलर
और कुछ नहीं है.
नहीं और भी है।
सर कहने का सर मेरे को जहाँ तक समझ आया ये है कि हमारे पास जितने भी कलर्स के बॉक्स हैं उनके अंदर और बॉक्सेस हैं जिनमें बॉल्स जानी है।
नहीं, मतलब ये नहीं है, मतलब ये है कि वन टाइप के Na बॉक्सेस हैं भाई.
यस सर यस सर।
1 1 1 1 1 1 Na बॉक्सेस हैं.
यस
ओके,
यस सर।
2 टाइप के भी सम बॉक्सेस हैं.
सर टाइप से मतलब डिफरेंट कलर ही है ना?
डिफरेंट कलर ही है. देयर इज नो, या तो मैं शेप दे देता जैसे मैंने पहले यहाँ दिया था, यहाँ पे मैं कलर दे दे रहा हूँ. ओके, बोथ आर सेम थिंग ना. महिमा, you understood or not? So to be,
सर महिमा गई।
हाँ
महिमा गई सर।
अच्छा, so just to
Sir,
see,
I did not properly understand the question, sir.
I'm telling you, there are boxes of different colors. Okay, suppose this box is of red color, मान लेते हैं, and then this ball, 10 different color balls are there. What is the color of this ball?
Red.
Red. Okay. Now you have Na balls and Na boxes in which it can fit. Am I correct?
Yes, sir.
Sautan?
Yes, sir.
Because this will not go to any other, na? So if I have to write N1, this will be N1. If you are happy with this, I can just explain you like this. N1, N1, okay?
Yes.
So in how many number of ways this can be done? It will be
So
N1,
GICNL.
C, N1. Simple mathematics problem,
Yes, yes, sir.
Yes.
right? And what will be omega 2 similarly? N2, C, N2. Like that? Like that? So what will be the total number of ways?
Multiplication.
So that will be omega is equal to omega 1 into omega 2 into dash dash dash, right? So I can write omega is equal to pi I if you agree. Pi A, any problem? Na, Cna, if you are fine with this.
Yes.
Yes, sir.
And this will be pi A. Now you understood why I went on to carry out those derivations,
Yes, sir.
the basic derivations involving Maxwell, Boltzmann and all. Na factorial, correct?
Yes, sir.
And if you go like this, what will happen? Please see. What will happen?
Sir, taking log.
So I will have to get S. So I will take log and you can see I will use a Stirling approximation without doubt. Yes or no? It is
Yes, sir.
Yes, sir.
so obvious. So just take for S, you just write KB ln of pi A into Na factorial by Na minus Na factorial into Na factorial. Am I right? So this will give S is equal to KB log of this will become summation. Multiplication will become
Yes, sir.
Summation.
summation. So what I should write? Log of Na factorial minus, I mean summation A. Log of Na factorial minus log of Na minus Na factorial minus log of Na factorial. Correct?
Yes, sir.
Apply the Stirling approximation. It will become S is equal to KB summation A. What I should write here? Na ln Na minus Na. What I should write here? Minus ln Na minus Na minus Na minus Na. Correct? X log X minus X. So plus Na minus Na. If you are comfortable, tell me. And minus Na ln Na plus Na. So this is the final answer. Just cancel whatever is getting cancelled. This is the answer. Understood, everybody?
Yes, sir.
Yes, sir.
Yes.
So this is the previous net exam that was. So is it a difficult?
No, sir.
But you have to
No,
keep
sir.
your mind very stable while reading the question. They will talk about ball, color, but ultimately it is just the distribution, nothing else, right?
सर पहला तो मुझे समझ आ गया था तब भी सर, पर सेकंड में मैं भी फंबल कर गया था उसमें।
So this is one particle, one quantum state और क्या है ना?
ये सर वो मुझे लगा कि ऐसा कैसे हो जाएगा।
Sorry?
सर एग्जैक्टली फर्मियान्स के बारे में कह रहा है डिफरेंट तरीके से।
डिफरेंट तरीके से मैंने शेप कह के पहले वही फर्मियान के बारे में मैंने कह दिया।
यस सर।
एक ताला एक चाबी फर्मियान ही तो है।
Link locks.
Right? So that's why logic is important, concept is important. Things may, may be different, but you can correlate always, right? So समझ आया भाई अच्छे से? Everybody got it?
Yes sir.
So the derivation that we have done in Maxwell-Boltzmann on fermion, that has already created a background in your mind, if you remember, of this sort. We have done this in another way, right?
Yes sir.
So that's why वो derivations मैं कराता हूँ कि that मैं हमेशा ये बोलता भी हूँ कि in some new situation you have to derive it from the scratch. Many times students think finally I have to use omega. Why sir is doing all this stuff? Why Stirling formula and opening of the brackets, this and that? And this time this question justified, because I have been doing this since 2009. But this time this justified that derivation is very, very important, and that is important for this exam also. Okay? चलो फिर
Yes.
मिलते हैं नेक्स्ट क्लास में बोसॉन के लिए. ओके, थैंक यू.
Thank you
Thank you.
sir.
थैंक यू सर।
Thank you, sir.
थैंक यू.